Hello everyone, this is Mr. Kazi coming to you from my virtual studios in beautiful Atascocita, Texas. And today I'm coming to you with another lesson on chemistry. And today's an exciting one because we're going to learn to do chemical nomenclature. And that's just a fancy way of saying we're going to learn to name the compounds. I'm excited about this lesson because if you'll buy into my system, you don't have to memorize a whole bunch of names or a whole bunch of things to learn to name hundreds, if not thousands, of chemical names. All you have to do is learn a few simple processes and general rules, and you'll be naming hundreds, if not thousands, of chemical compounds. So, without further ado, let's get started. In this lesson, you will learn numeric prefixes, the nonmetallic roots, common ions, polyatomic ions, and naming compounds. You will need, of course, a periodic table, unless you've memorized it, and that's great. And you will need a polyatomic ions table, and a little later in this lesson I'll show you how you can get that if you don't have one. And you must know oxidation numbers, covalent compounds, ionic compounds, and the periodic table. This is kind of something we need to know so that we can name our chemicals properly. One of the first things that we need to know about is the common metallic roots. And you want to make some flashcards or something to learn these. And they're also going to be listed on the polyatomic ion cheat sheet that I put together. And in a little bit I'll show you how to get that, okay? But we want to be able to look at these. Here are the common metallic roots. And you just kind of look at those. Really pay attention to the sulfur and the phosphorus roots, because really they're almost really not a root but the name. And it used to be that they used sulf and phosp, but I've never seen anything in the names that didn't use the full sulfur and phosphor. Our numeric prefixes are very important. Now remember, we only use numeric prefixes with a covalent compound, but we need to know these, okay? So we have mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. The common metallic ions. Now these aren't all of the metallic ions, there are more. I think I've even listed more on the cheat sheet. These are the most common ones that I use a lot, and so you will too. And the more you know about them, the better you're going to be at naming compounds. Polyatomic ions. Covalently bonded elements that act as a unit and have a charge. Now these are what I like to think of as elements that have come together, and instead of being a compound, they think they're an element. And so they act as one unit, and we treat them as one unit in most cases. Here's some examples: hydroxide ion, the carbonate ion, and the nitrate ion, and there are many more. And write this down. If you need a common polyatomic ion sheet, a little cheat sheet I've put together, you can pick one up here at polyatomicions.pdf. Just copy this whole URL and put it into your browser, and that'll take you there. And if that doesn't work, be sure to just send me an email at mrkazi@mrkazi.com. Alright, general rule for naming compounds. Most compounds are binary, and that just means that they are two parts. And so that's our number one thing to be thinking about there. In this general rule, most compounds are binary. They're made up of two parts: water's hydrogen and oxygen. Two parts. And even those with polyatomic ions, they're still really two parts. They're the polyatomic ion and the ion that they've attached to. So keep that in mind. And it's all just two parts. Alright, let's name some ionic compounds. In naming ionic compounds, write the full name of the cation and use the root of the anion and add IDE. That's pretty easy. You just take the full name of the cation, and then you take the root of the anion, and then add IDE. Here's an example. Sodium and chlorine come together and make sodium. There's the cation. Chloride. The charges of an ionic compound must balance to zero. Notice the sodium has a +1, and the chlorine has a -1, and +1 and -1 is 0. So we don't have to add any extras. They balance out perfectly. Voila. Metal ions with multiple charges. The oxidation numbers of the metal is indicated by a Roman numeral in parentheses. So some of those, like copper, you have copper 1 or copper 2, and we designate the difference between them by using Roman numerals in their names. Examples: you have iron 2, which then means the 2 in the parentheses means it's a +2 charge, and that you just have to memorize that or look it up on your sheet. And then we have iron 3. It's really that simple. Copper 1, copper 2. Fe2O3. Notice that the total charge on the oxygen is 3 times -2, which is -6. Remember, now the charges have to balance to 0. And so the iron, what's the iron going to be? Well, take -6 and divide it by 2, and we realize that that whole charge on the iron has to be +6. So divide +6 by 2 and get +3. And we have iron 3 oxide. Isn't that pretty simple? Polyatomic ions. Polyatomic ions are treated as a single unit, and you must know the charge of the ion. And you see there, ammonium NH4 has a +1 charge. So NH4 is a +1, ammonium. Carbonate is a -2. They don't balance. So to help balance it out, we make sure that we add 2 ammonium. Notice that. We had 2 ammonium up there to make sure that it's balanced. Ammonium carbonate. All right, let's name covalent compounds. In naming covalent compounds, and of course that's the same as molecular compounds, use the full name of the more metallic, followed by the root of the less metallic, and add IDE to the root. Use numeric prefixes to show how many. Now remember, we only use numeric prefixes on covalent compounds. With molecular compounds or the covalent compounds, we use numeric prefixes. As you go left to right, the compounds get less metallic. So the left side is metallic and the right side is non-metallic. Keep that in mind. Carbon is more metallic, so we'll put carbon down. Oxygen is less metallic, so we have oxide. Notice we took the OX, that's the prefix of the oxygen, and we added IDE, and carbon oxide. But there's 2 of them, so it's carbon dioxide. How about the next one? Can you name that before I put it up there? Nitrogen is the more metallic. Oxygen is the less metallic. But there are 2 nitrogen, dinitrogen, and there are 4 oxygen, so tetraoxide. Now note we drop the A. Whenever we end up with an A and an O next to each other, we usually drop the A. Practice time. Da, 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 da. All right, let's practice this. How about SF6? Did you get sulfur hexafluoride? Did you get lithium hydride? Very interesting about lithium hydride. This is a case where hydrogen is actually a negative instead of a positive charge. When hydrogen bonds with a metal, it takes on the anion instead of the cation. What about this one? Ammonium nitrate. 2 polyatomic ions coming together. Ammonium nitrate is a popular fertilizer. Now this one here, think about multiple charges for copper. And so we get copper 1 sulfide. Now it's copper 1 because sulfur has -2 charge. Notice there's 2 coppers. Well, if there's 2 coppers, that must mean that copper only has a +1 charge. And here we have sodium carbonate. And again, we check our charges. Carbonate is a -2. Sodium is a +1, so we need 2 sodiums to balance out. Got to make sure they balance. All right, be sure to check out MrKazi.com for PowerPoint videos and much, much more. There's handouts and a lot of other good things there. And be sure to subscribe to my YouTube channel. There are about 22 videos there. Go check them out. And y'all have a good day and happy ions. Valent and ionic bonds, the periodic table, and polyatomic ions. You need to be familiar with these. You need to know how to use the periodic table. Remember, that is your most important tool in the chemistry class. What exactly is an acid? Acids have at least 3 possible definitions. But for right now, all you need to know is that acids are compounds that release hydrogen cations, that's positive ions, when dissolved in water, when they are aqueous. And that gives us an acid. And here's an example. Hydrogen chloride when dissolved in water, gives us hydrogen ions and chlorine ion. And there we have it. It's an acid. There are two types of common acids. There are binary acids and there are oxyacids. So there are two basics. And of course, binary acids are aqueous solutions of binary compounds that produce hydrogen ions. And here's some examples. And naming binary acids goes as such. First, you use the prefix hydro, the root of the other substance, add the suffix IC, and then say acid. Here's an example. HCl. There's my H, so I say hydro. There's my chlorine, and the root for chlorine is chlor, so hydrochlor. Add IC, hydrochloric, and say acid, hydrochloric acid. Now, if you need to review that, rewind and go through it again. And here's some practice. And up in the right-hand corner, you see I wrote the rules. And remember to refer to your common ions sheet, your polyatomic ion sheet. Refer to that. It's an awesome reference. All right, HF. Let's name that. Fluor hydrofluoric acid. Again, we know it's going to be hydro and iod for iodine. Hydroiodic acid. Pretty simple, isn't it? Now, this one is a polyatomic ion. There are cyanide. And so we look up its root, and it would be cyan. And so hydro cyanic acid. Pretty cool. H2S. And we see sulfur. And so that would be hydrosulfuric acid. H with the Br, that's brom, and add IC, and we have hydrobromic acid. It's really just that simple. Now, let's look at oxyacids, or what was known at one time as ternary acids. Aqueous solutions of compounds contain hydrogen, oxygen, and a third element. And here's an example, H2SO4, and the third element is sulfur. Okay, oxyacids are named from the polyatomic ion. So, in SO4, we'd use sulfate. In NO3, we'd use nitrate. And PO3 is phosphite. And how these end is very important. So we need to know the polyatomic ion. Therefore, the reason we need to have the polyatomic ion sheet out. Or memorize them. Either one. Naming oxyacids. If the polyatomic ion ends in ATE, use the root of the third element and add IC, and acid. Use the root of the third element, add IC, and acid. That's if it ends in ATE. Let's try some. An example, HNO3. Well, NO3 is our polyatomic ion, and it is nitrate, so it ends in ATE, so we're going to add IC, and that would give us nitric acid. If the polyatomic ends in ITE, use the root of the third element and add OUS and acid. Again, it depends on the ITE knowing those polyatomic ions. Let's do an example. HNO2, there's our polyatomic ion, and it is nitrite, and nitrite ends in ITE, so add OUS. So nitrous acid. All right, let's practice a few. Up in the right-hand corner, I've put a little box of the rules, and we need our polyatomic ion sheet, and let's get started. H2SO4. Well, SO4, that's sulfate. It ends in ATE, so I'm going to add IC. So it would be sulfuric acid. Now look at that for a moment and just realize we took the root, sulfur, added IC, and said acid. Sulfuric acid. All right, H2SO3. Sulfite. And that is going to give us sulfurous acid. ITE means add OUS. HiO4, the polyatomic ion, is periodate, periodic acid. ATE means add IC. H3PO4, phosphate. ATE again, so we're going to add IC, phosphoric acid. And then H3PO3. PO3 is phosphite. ITE means OUS, phosphorus acid. Pretty simple, isn't it? Just got to remember the rules. All right, let's recap. Two types of common acids, binary acids. you take hydro, add the root of the other substance, and add IC and say acid. Oxyacid uses the polyatomic ion. Therefore, if it ends in ATE, you take the root of the third element, add IC and acid. If it ends in ITE, you take the root of the third element, add OUS and acid. There's our rules. That's how to do it. As usual,